So, in the previous lecture we looked at different types of polymorphism. So, we looked at conformational polymorphism, we looked at examples of conformational polymorphism, packing polymorphism, and then we looked at pseudo polymorphism. Now that we have got some idea about that we are able to get polymorphs by changing the crystallization conditions, let us look at the statistical probability or the possibility of the occurrence of polymorphs, that is how frequently are polymorphs obtained when we try to crystallize different kind of compounds. So, occurrence of polymorphs. So, there are some compounds which have been crystallized millions of times, but no polymorphs have been obtained. For example, benzoic acid, and then D-glucose, naphthalene. These three compounds, I am giving you just three examples. These have been crystallized millions of times, but no polymorphs have been obtained. Obviously, when these have been crystallized, these have been done at ambient pressure. So, pressure is another factor which plays an important role in polymorphism, and there is a field called high pressure polymorphism where you can actually apply pressure, decrease the volume which is available to the crystallizing molecules, and then when crystallization takes place and crystals are formed, they are actually formed under the application of high pressure. So, in the absence of high pressure, under ambient pressure conditions, that is at normal atmospheric pressure, when you have tried to crystallize benzoic acid, glucose, D-glucose and naphthalene, they do not form any polymorphs. On the other hand, there are some compounds, for example, carbamazepine. Carbamazepine has got large number of polymorphs, carbamazepine, and then we have got thiourea, we have got 2-thiobarbiturate acid, then we have got pyrazine 2-carboxamide. So, these four examples tell us that these compounds, they have give us large number of polymorphs whenever we have attempt crystallization, and even if today you try to do crystallize these compounds by changing the conditions, you might get different kind of polymorphs, and also you might get solvates, which is also very important as we realized in the pharmaceutical industry. So, and then there are some compounds, depending upon the amount of efforts you put into crystallizing those molecules, you will be able to discover polymorphs. So, there was one very famous statement made by a scientist called Walter Macron, who said that the number of polymorphs you get is directly proportional to the amount of time and money you invest in that compound. So, if you know that a compound is biologically very relevant, has got good pharmaceutical activity and is of importance in the treatment of a particular disease, then the industry has invested a lot of time and money to be able to screen the compound for all possible polymorphs. And this is something which Walter Macron did say, that you can get more polymorphs if you invest more time and money in that particular compound, trying to crystallize it under different conditions. The crystallization space is extensively sampled, and then you might be able to get polymorphs. So, there are compounds where substantial efforts have been put in and polymorphs have also been obtained. Because now this particular phenomena has got relevance in the pharmaceutical industry, and a large amount of efforts is put in either manually via a team or using different kind of solvents and different kind of apparatus. This has been partially replaced by so-called robotic crystallization, where you have got a robot where which has got chambers made, and you can at one time put in say around 500 to 700 crystallizations using small amount of the compound. Say the particular compound is a very important compound in the drug industry. Say you have got 20 to 30 mg of it. Now you actually put say 1 or 2 to 3 mg in small regions of this robotic space which is available, and then the robot is actually programmed to put in the necessary solvents in the right amounts, and then once the crystals is formed, it will take the crystal and put it on the diffractometer and check the unit cell for you. In this way, we are able to extensively screen a large number of crystallization conditions, a large number of crystals, which is done using robotics process. But then again, this is a lot of efforts and a lot of experimental inputs to be able to get polymorphs, and this is where the computational efforts have been extended to predict polymorphism. So computational investigation of polymorphism. And when you are doing the computational investigation, we need to keep in mind that all the calculations are being done primarily to start with at 0 Kelvin. That is, we are ignoring the role of temperature in the crystallization process, and also the fact that temperature does play an important role in giving you different kind of polymorphs, and the overall stability, the order of stability of polymorphs can also vary depending on the temperature of crystallization. But to start with, computational investigation of polymorphism has been actively pursued, where there is a very important research area which has been developed, which is called crystal structure prediction, where we hypothetically generate a large number of crystal structures in a small energy window, say between 1 to 2 kcal per mole. A large number of hypothetical crystal structures are generated in a narrow energy window. And out of these hypothetically generated crystal structures, say we take the top 100 low energy crystal structures, and then we are able, and we know that they lie in a narrow energy window. Now we can go ahead and crystallize that compound and see whether we can experimentally realize the low energy forms of that particular compound. And most of the times it is not the most stable one which is sampled, it is the kinetic form which is slightly higher in energy compared to the thermodynamic form, which is actually experimentally realized. So this field of crystal structure prediction is very, very interesting, because it allows us to a priori predict the different kinds of polymorphs, or what are the energetics associated with these polymorphs which can be formed, and you can actually look at the hypothetical crystal structure of these particular polymorphs, and then if experimentally you realize these polymorphs, then it is a win-win situation, because you predicted something and now you also experimentally realized it, and that vastly decreases the amount of experimental resources you actually put into the field of polymorphism. Okay, so whatever you invest, that amount of money is actually reduced substantially if computational resources are also developed to investigate polymorphism. So now let us go a bit more into the details of how do we characterize polymorphism, because characterization of polymorphs, and there are a large number of techniques which have been developed in the past 2 decades, because the field benefited tremendously by the development of different kinds of techniques which contributed towards the understanding of the phenomenon of polymorphism. So to start with, we will first look at the basic technique which we have already explored, that is called the optical examination of crystals. Under a microscope. The number 2 technique is thermal methods of characterization, where we look at a technique called differential scanning calorimetry and combine it with another microscopic technique which is called hot stage microscopy, HSM, DSC is differential scanning calorimetry, and in order to characterize the amount of solvent which is present in a crystal, we can do a thermogravimetric analysis, which we call as TGA, which actually looks at the weight of the crystal as a function of temperature. So we will look at some of these aspects. Number 3, the most important technique for characterization, the most important technique for unequivocal characterization of polymorphs is single crystal X-ray diffraction or powder X-ray diffraction to start with. So these techniques are also very important. Then there are spectroscopic techniques, for example IR, Raman and solid state NMR, to look at the local environment and the changes associated with the bonding in the local environment that get reflected in the spectroscopic properties now of these solids, because polymorphs are characterized by different arrangements of the same set of nuclei. So depending upon the kind of interactions the different nuclei experience, it will also have an effect on the spectroscopic properties, and this can be investigated at a very subtle level by exploring the subtle changes in chemical environment with concomitant changes in the chemical bonding associated with the functional groups. These spectroscopic properties can be extremely useful to monitor. And then we can look at computational approaches, for example the lattice energy calculations, and then we can do the physicochemical properties, which is different for different polymers. For example, we can do IDR, which is called the intrinsic dissolution rate, the solubility, the equilibrium solubility, which is a measure of the bioavailability of the polymorph of interest. So, and I already told you the melting point, the lattice energy and the density is going to be different. So, we have already looked at the optical examination of crystals, we have discussed about it. Now let us look at the thermal methods. Now thermal methods are extremely sensitive to the characterization of polymorphs, and the first thing we need to keep in mind is when you are doing a experiment, a DSA experiment, the thermal history of the sample is very important. The thermal history of the crystals or the crystalline solid is very important. That is how you have prepared your crystals. That is how were the crystals obtained. Whether the crystals were obtained in the kinetic conditions or thermodynamic conditions, and at what temperature were the crystallization done. So the thermal history of the crystals is extremely important. And here what we do is that we essentially do a DSC experiment where we actually heat the compound, and as a function of temperature we look at the heat flow, and we start with say room temperature, and then say at 130 degrees centigrade the compound melts. So this corresponds to the onset temperature is the melting point. So the onset value is the melting point of my substance, of my solid substance, and the area under this curve is associated with the enthalpy change of going from solid to liquid, and the ratio of this delta H, when delta H by T, when you take this quantity, it gives you the entropy change associated with the process. And because these experiments these are being done in hermetically sealed aluminum pans. So when the process of melting takes place, the temperature does not increase. Whatever heat flow happened to the system goes in melting the compound only. So this delta H can be equated to Q by T, where Q is the amount of heat which is absorbed by the substance to melt, and therefore the temperature does not increase, and that is why these processes are endothermic, because heat is absorbed by the substance to melt. On the other hand, now say the compound is melted, now you stop the process of heating further. You obviously assume here that the compound has gone from the solid to the liquid state, it's a melt, and now you perform the reverse experiment where you now start cooling the sample. And when you start cooling it, you will see that at the temperature at which it should have crystallized, the crystallization does not take place. The crystallization happens at a slightly lower temperature. So there is a hysteresis in the process. There is a slight delay in the process. This is called hysteresis, and then the crystallization takes place at a particular temperature, and then it comes back to the initial state. So this is an ideal representation of a DSE. You have melting, and then you have the recrystallization. In most of the experiments, the recrystallization process does not happen at the time of the experiment. This is because the melt does not recrystallize. There is a hysteresis, there is a thermal arrest. It's like more supercooled liquid, and it is only after enough time has been given, that means almost when you have given the conditions of thermodynamic equilibrium to be established, that the melt now slowly converts into the solid state. So many times it has been observed that you keep the melt in the pan, the sealed pan, for around 24 hours to 48 hours, and then it is obviously come down to room temperature now, and you leave it for 24 to 48 hours, and then when you take it out, you will see again the solid. So definitely when you had brought it back to the initial room temperature, it did not become solid. You left the pan for 1 to 2 days, it became a solid. So it has now converted into the solid phase. Now the next question is that did it convert back to the initial phase, or has it converted into a new polymorph? And that can be determined by again doing the DSE experiment. Now when you do the DSE experiment again, you will see that it will now possibly melt at a lower temperature. Say it melts at now 120 degrees centigrade. So now the melt has converted into another polymorph. So the initial polymorph, say I can say as P1, and now you have got another polymorph P2, and the melting points are different. Another one was 130 degrees centigrade, another is 120 degrees centigrade. So the melting point is different for the two polymorphs, and this can be very clearly established from a DSE experiment, which is very sensitive to the solid state formulation of that particular substance, the solid state structure. Similarly, you can now actually follow up with these events of say melting. So say you have got the solid to liquid melting, and then the liquid back to the solid. This process is taking place now. From the liquid it goes back to the solid again. Now this can also be followed visually using hot stage microscopy, where you have got an optical microscope. You have got the plate on which you have got a plate on which you normally examine your crystals, but now instead of that particular plate, you now put a hot plate, and then you actually close the hot plate, and then you do the heat, and then you heat the plate, and then you can see that as the crystal melts or the solid melts, you will physically be able to visualize the changes which happens on the hot stage plate. So the hot stage plate combined with the optical examination allows you to see the changes which are happening in DSE at a more physical level, with more visualization. You can visualize all the effects which are happening, and you can follow this process over multiple heating cooling cycles. So the DSE experiment itself, to start with, need not be stopped after one complete cycle of heating and cooling. You can actually continue this over at least 2 cycles. So you can go from heating, you can first start the first heating cycle where you go from heating and you melt it, then you again bring it back, you cool it, and again you can heat it, and again you can cool it. Now this is one cycle, one complete cycle. where you have heated, cooled it, and then you do not stop the experiment, you again do heating and cooling, that is a 2 complete cycles. And this allows you to understand more deeply whether any possible events have happened where one polymorph has converted into the other because you had a melt, and that will allow you to see whether you actually accessed a new polymorph or not, and how does it look like, and so on and so forth. So DAC combined with HSM gives a 1:1 mapping of all the events which are taking place. Another very interesting thing which can be seen in an HSM is if you have a solvent which is included in the crystal structure. So say you have got a solvatomorph and it includes say acetone or tetride of furan or ethyl acetate, methanol, benzene, then you will see that when the crystal is being heated at a particular temperature, desolvation takes place and bubble formation happens. So you have the crystal and you will see nice bubbles are being formed, which actually correspond to the solvent molecules and which are being released into the environment. So you see the solvent molecules being released into the environment, so there is a loss of solvent, and then the anhydrous form melts at a particular temperature. So you have the desolvation followed by the melting of the anhydrous form of that particular compound. So this thing also you can see very clearly in an HSM experiment. So DAC and HSM actually go hand in hand, and if you would like to quantify, say you have got a solvatomorph, and if you would like to quantify the amount of solvent loss as a function of temperature, then you do the TGA, that is the thermogrammetric analysis, where you actually measure the weight, the percentage weight change as a function of temperature, and then you will see that you get this kind of a TGA response, a thermogrammetric response, where you will have some percentage of weight loss, say at a particular temperature here, and then so you will have this much of weight loss, okay, when you reach this particular temperature, say x degree centigrade, and then from here you will further have more weight loss, then here this remains fixed, and again you have more weight loss here taking place. So this is the next set of weight loss you have. So this is W2 weight loss, this is W1, how much amount of weight is being lost as a function of temperature. And you can actually map this experimental weight loss with the theoretical weight loss, because you know how much of substance you started with, you know which solvent is coming out, so theoretically you know how much would come out, and you know what you started with, so you can actually calculate the amount of loss which should have happened and match it with the percentage weight loss from experiment, and that allows you to unequivocally again establish the amount of solvent loss taking place as a function of temperature in a thermogrammetric experiment. Another very important parameter when you do these particular experiments, that is DAC or TGA, is the scan rate. You can actually heat at very fast rates, or you can heat at slow rate. Normally the recommended rates are 10 degrees centigrade per minute, 5 degrees centigrade per minute, but in some cases you can also do 100 degrees centigrade per minute, which is extremely fast heating, and you can also do at slow rates like 1 degree centigrade per minute, 2 degrees centigrade per minute, and so on and so on. So slower is the rate of heating, more is the control over the process. And also if you also cool, so heating and cooling should happen at the same rate for a given experiment. You can also combine this if you want, you can do at a fast rate and then cool at a slow rate, but slow rate of cooling is also encouraged, because then the chances of getting the solidified mass is high, because you are again cooling it very slowly, so you're kind of trying to maintain the thermodynamic equilibrium that can favor the formation of the crystalline phase when you cool it at extremely slow rates. And the same thing when you want to do an HSM, you would like to see that the HSM experiments are also being done at very slow rates, and there you can again do it at 1 degree centigrade per minute. So this is a very, very important factor when it comes to deciding the DSC, the rate at which you want to do the DSC experiments. And there are much more complicated processes which happen in DSC experiments. For example, there can be a solid to solid phase transition before melting. So you start with one particular phase, it can convert into another phase, and then that particular phase melts. Okay, so you can have a solid to solid phase transition, and then that particular form can melt. So if you have a solid to solid phase transition, that is referred to as enantiotropic. The two polymorphs are enantiotropically related. Whereas if you have a set of polymorphs, say A and B, and each polymorph melt at its own characterization melting temperature, that is, each polymorph is stable over the entire range of temperature before it melts, then these two polymorphs are monotropically related. Okay, A and B. We will look at these aspects a bit more detailed later on, but so this is to tell you that the thermal events of characterization is extremely important in the process of crystallization. And now we go to the next technique, which is the most important technique, that is single crystal XRD. So single crystal XRD now is a highly automated technique. You have to put in the crystal and you collect diffraction data, and the necessary software is there which will integrate your data and also determine the structure, it will refine the structure, and all the steps it will perform systematically and give you the final crystal structure. This is in itself an independent research area which we call X-ray crystallography, which is the science of determination of crystal structures. But today single crystal X-ray diffraction is highly automated, and the final crystal structure tells you that you have got one particular polymorph with an independent set of unit cell parameters and something called a space group. For example, I am just giving one example, P21 by C, which is called a symbolic representation of a space group. If you are not aware of it, need not worry about it, but we call this quantity as a space group. So one particular polymorph has a particular set of lattice parameters, another polymorph, say P2, has another set of unit cell parameters in a space group, and these are different for different polymorphs. And it is not necessary that you always need to have the same space, a different space group. You can also have the same space group but different lattice parameters. In other words, the molecule can now choose another arrangement with a different box, a different unit cell, but still maintaining the same space group. So different possibilities exist, but what is more important, it gives you the atomic positions and the three-dimensional connectivity. The three-dimensional connectivity between the atoms to form the molecules, atoms to connect to give molecules. And you can look at the three-dimensional connectivity and the overall three-dimensional arrangement, and because the three-dimensional arrangement is going to be very different, that will allow you to characterize from X-ray diffraction. The next important technique, which is parallel to single crystal XRD, is powder X-ray diffraction. Now this is a very, very important technique because this is called the fingerprinting response of a particular phase. So this is like a fingerprint response. So just like infrared spectroscopy is a fingerprint for every organic molecule which you have synthesized in the lab, powder XRD is a fingerprinting technique. It's like a fingerprint for a particular phase or a particular polymorph of a compound. And if you record the powder XRD of a particular polymorph, say P1 of any compound, say which you have synthesized, the intensity as a function of 2 theta, you get a set of diffraction peaks. And now when you record it for another polymorph, you will get so now you can see this is a very qualitative way of representing it, that some of the peaks are same but most of the peaks are different. The red one represents P2 and the green one represents P1. So because the solid state arrangement is different, the diffraction events which are happening corresponding to the different planes in the crystal will also give rise to an interference pattern corresponding to the different planes which will actually come at different 2 theta values. So the 2 theta values are going to be different for different polymorphs, and that is the reason why this technique is called a fingerprint technique for every polymorph of a given substance. And what is important is that once you determine the unit cell parameters, say P1 and P2, you can do something called a profile fitting, which can actually characterize the phase unequivocally. Now, because you know the unit cell parameters and the space group for the P1 phase, if you run the calculation and if you do the modeling of this profile, you will actually generate a theoretical or simulated powder pattern where the 2 theta positions calculated will exactly match with the 2 theta experimental positions. So, there is a peak to peak correspondence between the theoretical powder pattern simulated from your determined crystal structure. So, once you have solved the crystal structure, you can actually generate a simulated pattern or a theoretical pattern, and then you can compare it with the experimental pattern and do a peak to peak correspondence. Then you can further characterize that phase on which you have recorded the powder pattern unequivocally by fitting the profile to the experimental lattice parameters for a particular phase. And then once you fit the profile, you can then see the difference profile. The difference profile will come here. The difference profile will be essentially like a baseline which does not have any peaks because the difference is equal to 0. So, this is essentially featureless in the sense that the I observed minus I calc is approximately equal to 0. And if this is not equal to 0, then it means that you have unaccounted peaks either in terms of intensity or in terms of the 2 theta values, and it possibly indicates that either you have not modeled your phase accurately or there is another phase which is present in your powdered sample. But if you do it on the crystals, chances are you have and you have checked all these crystals slowly by doing the unit cell determination, and now you take these crystals and record the powder pattern, then the chances are almost near 100% that you have got a pure phase because you have checked all the crystals of that phase by the unit cell determination. So, powder XRD allows us to unequivocally establish the phase purity, and in case of concomitant polymorphs, you will see that both P1 and P2 are present in the bulk phase. So, you have got the bulk phase, you will see both the polymorphs P1 and P2 will be present in the bulk phase as well. So, with this we can characterize polymorphs using these different techniques. In the next lecture, we will go and further look at other aspects of polymorphism. Thank you.